Hello class. So in this recording, let's look at some problems and examples related to the latches and flip-flops material that I covered in the last lecture. Okay. So I will. So this is where these are the topics that we have covered. We went through all this. I'm skipping past the slides. And I will stop at, well, slide number 49. Okay, so slide number 49 is the first numerical that we will do related to the SR flip-flop. Now this is an example from the textbook, so fortunately you will have access to the solution. It is a complicated problem, so I'm going to also spend some time on this. While the answer is, well written in the textbook, I think I can add a little more also to help you understand. So, what is the problem? The problem is that the example states that we are trying to implement a CMOS SR flip-flop as shown in figure 15.4, which is this figure, right? So this form of the clocked version of an SR flip-flop is what we are trying to implement. So again, there are two inverters here, as I've talked about already. Q1, Q2 is one inverter, Q3, Q4 makes another inverter. Similarly, Q5, Q6 makes this AND gate on the set line, and Q7, Q8 makes this AND gate on the reset line. Right? We said both the clock has to be high, obviously, and the set has to be high for a change to happen. And by definition, when a set is high, Q output goes to 1. Similarly, when reset is high, Q bar goes to 1. Q goes to 0, right? So that's the basic logic. I also described to you that if we start with a reset state, that means Q is 0 and Q bar is 1. From there, if you try to put a set input to the flip-flop, then it will flip. It should flip, because with the set input and the clock input both on, this point, which is the input to this inverter consisting of Q3 and Q4, that will go low, because you know that the MOS AND gate operates like a pull down network, and the output goes low. So this particular output here goes low, and that output, which is also VQ bar, that is going into the base of Q4 and Q3, and so when the input goes low, you expect the output of that particular inverter to go high, because it's an inverter, right? So that is the operation that we are attempting. Okay, so the question here is, if all that has to happen, given that the transistors have these properties, so let's look at part A. Determine the minimum value required for this W by L ratio. So the 4 set reset transistors, okay, the set reset transistors means Q5, Q6, Q7, Q8, right? These are the set reset transistors, along with, of course, the clock. So you should have said that, but he's not saying it. So the 4 NMOS transistors in the set reset circuit have equal W by L ratios. So they are all, same W by L. But what is that W by L is the question. So determine the minimum value required for this W by L to ensure that the flip-flop will switch. Okay, so let's look at part A first. He has given some values for mu n cox, which is nothing but qn, right, or qn prime. So qn prime equals 4 times qp prime, which is 300, and then vtn and vtp are given. vdd, this voltage is 1.8. The inverters also have been given, the inverters only, right, which is not these transistors, but the Q1, Q2, Q3, Q4 inverter transistors. They have these values for W by L. So W by L for the inverters are given. The P has 4 times W by L N, and 4 also happens to be this multiplier. So from that you should be able to say that the inverters are all matched, right? Because you know the condition for matching. Qn prime W by L N should be equal to Qp prime W by L P, and also Wp by the width ratio, because the length is always the same, the width ratio should be mu n by mu p. If these conditions are satisfied, then the inverter set is called matched. And the big deal about having matched inverters is that the switching point, that means the point at which the transition happens. So if you have a low input to the inverter, then you expect that the output will go high, right? So previously, if the inverter output was low and you apply a low input to the input side, then the inverter will switch. When will that switch happen? When Vm, the switching point, which is when the input voltage equals VDD by 2, right? The switching point is Vm. Vm is nothing but the input to the inverter. If the input to the inverter falls below VDD by 2, that means if the input to the inverter is half the supply voltage, that is recognized as a low input to the inverter, and so the output will become high. So the switching will happen at that point. All right. So we have agreed that it's a matched inverter set. We agreed that the switching will happen at Vm. Now the question is, how do we use this information to find the W by Ls? Now, as you can see from as you go through the example, the one thing that is done to set up an equation to solve for W by L is to create an equivalent circuit, right? Now this is just this part, the leftmost part of right? Only this part, right? So we are focusing on this part for the moment. Whatever we find here is equally applicable to the other side because they are all, matched. So let's focus on just this portion, the left portion. And here, what he does is, this Q2 has all these in series, right? So he takes the combination of these two, which have the same W by Ls, and converts them into an equivalent. So this step is important, okay? So the equivalent transistor has a W by L which is half the W by Ls of the individual transistors. So this is a bit like connecting capacitances in parallel, right? When you are there, capacitances in series. When you connect capacitance in series, the total capacitance is half, right? Similar to that, the W by L of the series combination becomes half. So he replaces these two with that, and then he's still got Q2. So here he analyzes the conditions as this starts to conduct, the Q5, Q6 conducts, and VQ bar, which is the voltage here, goes low, starts to go low, right? When this goes to, it's going from from VDD, which was originally the value, because it was in reset condition, Now it is going low, and at some point it will hit VQ bar equals VDD by 2. That is the point of the switching, right, where it happens. So what W by L value for this equivalent will help it switch, will make it definitely switch. So as you can see, what he does is he equates the two currents in this equivalent drain circuit and the actual Q2 drain circuit, because they are the same, right? ID2 equals IDEQ, because they are connected like this in series. And this is kind of a no load condition, so that's what we assume, that we think that the current is flowing, same current is flowing in the two drains. So notice how he sets up the equation for IDQ equals ID2. And one more important thing is that both these transistors are in the triode region. Why are they in the triode region? He hasn't explained too clearly, he just says it's there, but I have tried to give you the conditions. So for example, PMOS, right? Consider this PMOS transistor. Its condition for triode is V drain to gate, right? So the drain to gate has to be greater than VTP. Now what is the drain to gate? It is the VQ bar, which we are saying is VDD by 2, and VDD is 1.8, so half of that is 0.9. So this voltage is 0.9, drain to gate, and gate is kind of at 0 or grounded. So VDG is greater than 0.9 is greater than 0.5, so the condition is satisfied. Similarly for NMOS, VGD has to be greater than VTN. So what is V gate to drain? So this voltage is what we need, gate to drain of this NPN, right? So how do you find that? So we know this point is already at VDD, so that's 1.8. We know this is half, 0.9. So this is point A with respect to ground is at 1.8, point B with respect to ground is at 0.9. So we can say this with respect to this, or A with respect to B, is the difference, right? 1.8 minus 0.9, so that's also 0.9. So this 0.9, which is V get to drain, is greater, which is 0.9, is greater than VTN, because VTN is 0.5. So thus we can say that both conditions are satisfied, and the two triodes, the two transistors, this equivalent transistor and this, are in triode mode. Hence, if you apply the proper triode, proper drain current formula, which he does, and he shows it to you, if you apply the proper drain current formula, on one side is the NPN transistor formula, the other side is the PNP transistor formula, and they have slight difference in their formulas. So if you apply the proper formulas, you end up with a value for W by L, which comes out to be 0.54 by 0.18, right? You can see that. And once you find that for one transistor, you can find that for all transistors, because the four they have same W by L. The other point, part B, is also interesting. Now we are asked to find the minimum width that the set pulse must have. So think of the set input as a pulse, right? It goes up and stays up like that. So what is the width of that pulse? So what does he say? He says that the value calculated to guarantee that the flip-flop will switch. Okay, the minimum required width of the set pulses consists of two components. The time for VQ bar in the circuit to fall from VDD to VDD by 2, and the time for the output of the Q3, Q4 inverter to rise from 0 to VDD by 2. So two things have to happen. The input voltage has to fall by half, the output voltage has to rise to half of the final, right? So these two times have to be found, and then if you add them up, you will get the total time. Okay. So I will let you look through how he finds the two times. It's shown in the textbook, and finally he adds the two to tell us that 82.3 picoseconds is the minimum time required. Okay, so I've taken 15 minutes to walk you through this because there's a lot of complex stuff. Now the time business is similar to what we have already seen, where we find, t p to tphl and then tplh. So these formulas are all used previously, so I'm not going through each one of them. But the bottom line is you will find TPHL and then TPLH, and then you add the two. Okay. If you have any trouble understanding the example, please write to me or talk to your co-faculty, because without understanding this, you might run into issues in the homework and in the exam and all that. Okay, so make sure you go through each step and clearly follow what is being written in the notes. Okay, let's continue, and let's look at the next numerical, and this is exercise 15.1 from the textbook also. So the previous one was an example, this is an exercise. Now this exercise is slightly different from what you actually see in the textbook, because I picked this from a different edition. So the values, the parameters for the inverters have changed. Previously there were 18 micrometer process. This is a 65 nanometer process, so it's a much smaller width of or length of the substrate, so it's a bit of a more advanced CMOS. But the example, the logic is still the same. So all this is given, and the inverters are again, the inverter transistors are still matched, because here you will see there is a factor of 3 that multiplies this to this, and that 3 also appears here. Okay, so it's still a matched set of inverters. The one other thing of importance is that the VDD has dropped to 1 volt, and the VTN, VTP have dropped to 0.35. Previously this was 1.8 and this was 0.5 compared to the previous example. Now they are lower. Other than that, everything is the same except for one very important change. So here he says this portion, right, is what we need to also worry about. Previous example, it was said that switching has to be achieved, when the phi and S are just at VDD. So because we will apply the full voltage to Q5 and Q6 to call them a high. Here, for some strange reason, we are not applying the full VDD 1 volt, but we are only applying 0.5 volts. And the question is it still possible to switch at this? That is the difference between this previous. Here we never bothered to think about what voltages are applied, right? We just assume it's always VDD for switching. Here he says make sure that the input voltages, or the voltages applied to the SNR, SN phi, is actually VDD by 2 and not just the full VDD. So the funny thing that happens is, previously when we equated the two drain currents, we proved that both of them were in the triode region, and so we could apply the triode formulas. Here what happens is, because of the lower applied voltage, the NMOS stays in saturation and the PMOS, that is this, this is in triode. Okay, so two different conditions, one saturation, one triode, but then you still do this formula to solve for it. So I've done this uh, in my PDF, let's follow along. So the drawing is the same, and the other principle, that you take the Q5 Q6, convert it to a Q equivalent, that is still the same. I'm applying the same principle. The only difference is, in the previous exercise you found that Vs equals VDD, V5 equals VDD. Here we drop that by 2, and the rest of it will be the same. So when V5 equals Vs equals VDD is equal to half volt, then automatically Q equivalent, this Q equivalent will be in saturation. Why? Because this voltage is half volt, this voltage is half volt. That means the net voltage at this point between this and this, which is the gate to drain, is 0, right? And one of the conditions is, if the gate to drain is less than VTN, which is 0.35, then it is in saturation. Hence, Q equivalent is in saturation. In the previous example, we saw that that was also in triode. So we use the triode equation. Now, Q2, you can check, still stays in the triode region, right? This Q2 is still in the triode. This is in saturation. So I take the saturation equation for Q equivalent, write it like this, which comes out to be 2.53 W by L of 5 and 6 transistors. For Q2, I write the drain equation, the drain current equation. It comes out to be a good 180 microamps. So this 180 micro equals this. That gives us W by L as 71.1. So you notice that the W is much higher than the L in this case. In our previous cases, it was only 3 or 4 times, right? But here, it's a lot higher, 71.1. So that is an example. Make sure you understand what I did there, and you can follow along. Okay. Next example, next is a problem from the back of the chapter, 15.2. And here we are asked to sketch the logic gate implementation of an SR flip-flop, not a clocked, but just a regular SR flip-flop, utilizing two cross-coupled NAND gates, right? So in the textbook, we already saw how you can connect two cross-coupled NOR gates to create a latch. But here he's telling us, use two cross-coupled NAND gates to create an SR flip-flop. Clearly label the output terminals, also provide the truth table. Okay? All right. So let me see if I can show you the solution. So here's problem 15.2. Okay. So this is the flip-flop we saw with NOR gates, right? We've seen this in the textbook. I think we've seen it. Yeah, let me check. Yeah, we saw the SR flip-flop with NOR gates. So the same thing has to be now implemented using NAND gates. So if you look at the output and try to write the logic equation, the output of Q is R or Q bar, right? Q bar comes in like this, R or Q bar. So Q equals R or Q bar, or you can put the complement on the Q and say it equals R plus Q. Okay. So that's just something to help us do the rest of it. Now another thing to note, we know that NOR and NANDs are they have some equivalence, right? What is that equivalence? So if this is your NOR and you have the two inverters here, that means if you take A and invert it and B and invert it and put it into a NOR, you get this A bar plus B bar. Now A bar plus B bar is also AB bar, right, by De Morgan's laws. So if you take the same, this logic or this equation as the output and you get this AB bar, that also means it's A bar plus B bar, right, because they are the same. Now how do you get this AB? You can put a NAND gate with A and B as the input as an inverter at the back and make it AB bar. So really this equals this, right, because they both satisfy this equation. So something like this is what you use to start guiding you as you develop your. So the NAND gate that we have to find consists of 3 steps. First I find this, then I go to this. So you can say it's one, first start with this, second, third, fourth. So 4-step answer to the question. Okay. So first, what am I doing here? I am trying to recreate the same equation that we have here, right, as the equation of the NOR version that we've already been shown in the textbook. So this is just this, and you're getting the output as shown here. So from here we do a few tricks. Okay, so what I've done is I've taken the R and this Q and Q bar, I've flipped it. So Q bar goes to the top, Q comes to the bottom, and this Q input is inverted before it goes into the OR gate, NOR gate. Okay, well this is just an OR now because the NOR went away, so we are creating 2 OR gates instead of NOR gates. But to do that we have to do one trick, first of all, which is the flip these and then put the little circle here to show an inversion. Now what is the output? The output is again same as this. It's Q bar equals R plus Q bar. Okay. So this and this are the same because we are getting the same output. Next, let's go down to this step. So here what I'm doing is instead of giving R and S, I'm giving R bar and S bar with an inversion before these two enter the OR gate. Okay, so again the output is R bar, sorry, Q bar. Remember, we put an R bar input, flip it or invert it, so it goes in as an R. Similarly, Q goes in as a Q bar. So Q bar is R plus Q bar, which is the same as this. Finally, we come to the last step where we take the 2 inversions at the inputs and put them on the output. So these OR gates become, these OR gates become NAND gates. So this and this become NAND. Now you'll notice that the output Q bar is R bar times Q, which can also be written as R plus Q bar, right, by this law. So again we have this Q output equals the same as we had for the NOR, right? So you can say that this NAND gate version of the flip-flop is exactly the same as the NOR gate version of the flip-flop. Okay, thus we can say that we have taken the original NOR gate and created a NAND gate version of the SR flip-flop. Of course, we have inverted inputs here. Here we only have R and S, but here we have R bar and S bar. So you will need inversion stages prior to this if you only have R and S signals, but we have answered the question that is required. Okay, all right. Clearly label the output terminals and the input trigger terminal. Provide the truth table. I haven't done that. I'll leave it to you to solve it. Okay, all right. We come to one more example. let's see, how many more do we have? So we have this, then we have one problem on D flip-flops, and that should be it. Okay. So here, this is a problem from the back of the chapter, problem 15.3, and is pretty much similar to what we have seen previously. So there's not a whole lot that's going to be new. But the first part of the problem is actually kind of a derivation. Okay. So the flip-flop, RS flip-flop is still the same. It consists of two inverters. 1 and 2 is one inverter, 3 and 4 is another inverter. We have the SN phi going in through an AND condition. Similarly, the R and phi, the clock, is going through is another AND condition. So for such a flip-flop, show that if each of the two inverters uses matched transistors, that is W by L P equals mu N by mu P into W by L N, right? So they are matched. Then the minimum W by L that each of the Q5 to Q8 must have, so that switching occurs, is 2 times W by L N. Okay? So whatever is the W by L N here used for the switching inverters, if you take that W by L N multiplied by 2, then the minimum W by L for 5, 6, 7, 8 is twice of this W by Ln. Okay, so if we have to prove that condition, and if you go and look at some of the examples we have seen already, you will find that it satisfies that condition. But here we have to prove it. Okay, so that's one part. The second part of the story is, so the sizes of all the 8 transistors are fabricated in a 0.13 micrometer process, for which mu n equals 4 mu p. Okay, so give the sizes of all 8 transistors. So we are asked to provide basically the W's, right? We have to give the size of all the 8 transistors if the flip-flop is fabricated using a 0.13 process. That means L will be 0.13. Use the minimum channel length for all transistors and the minimum size. That means W by L equals 1 for Q1 and Q3. Okay, so he's given us some funny conditions. Well, basically he's saying take W by L equals 1 for Q1 and Q3, which are the N-type transistors in the inverter. So that means this W by Ln is 1, right? Because these are the two N-type transistors in the inverters, and he gives us that data here. So using a W by L equals 1 in the problem, in the equations, and we don't have to even increase the channel length, just use the minimum channel length for all transistors and the minimum size also, W by L. Normally we take W by L is equal to twice the minimum, right, in solving some of these problems, but he says just use the same. So with all this, find the size of the 8 transistors. Okay, interesting example, I think. So let's look at 15.3. Okay, so again we are going to use the relationship ID equals ID2 in the triode region, right? Because here there are no funny inputs which are only half the VDD and all that, right? Like one of the previous problems we solved. So we can assume safely that phi and S are, the inputs will be at the proper high, which generally means VDD. So under those conditions, we know that both the equivalent transistor, equivalent of the two MOS transistors which form the AND circuit, those are in triode, and the other one, Q2, which is this one that we consider, is also in triode. So under those conditions, if you equate the currents, just by writing their equations for the drain currents, right? This is the general form of the equations, and since we are given that Tn equals Tp, generally that's the case, which also means that this half Kn W by L, right, this portion, which is also known as just Kn, this is half Kn prime W by L, is just Kn. So we know that this Kn equals this Kn. This is also Kp prime, right? So these two parts are equal because of this. So if you take Vtn and change it to Vtp, then all this is the same on both sides, right? So this and this goes away, and then we are left with this equals this, which is what I'm writing here. Okay, so again, there's Vtn here in this formula on the left side, there's Vtp on this side. Since they are equal, if you make them equal, then this whole thing and this thing cancel on both sides, and you end up with this relationship. So if this equals this, then WILP, so basically this is one relationship, okay? Also WILP is given to be this, which means WP by WN is this ratio. So if you take this equation and equate it, right? So you're going to end up with W by L 5 by 6. Remember, L's are the same, right, in this formula here. So take out the L's, and you know the W P by Wn ratio is mu P by mu N. So if you put all that together, you will end up with W by L 5 by 6 equals twice W by L N. So this is the what we were asked to prove, and that's what we have proven. Okay. All right. The next part of the equation gives us these values, right? W by L 1 by 3, which is W by L N, is 65 by 65 is 1. Similarly, W by L 2 by 4 is this ratio into this, right? And mu N by mu P equals, so this whole thing is 260 by 65, right? Because we are told that mu N equals 4 mu P. So if you put, sorry, this was the previous, yeah. So if you put 4 times on the numerator, 4 times 65, right? This is 4. So that becomes 260 by 65, and hence the ratio itself is 4, right? Lastly, W by L 5 to 8 from here is 2 times W by L N, which is 65 by 65 into 2. So that gives you 2. Okay. So these are the answers to the numbers part of this problem. Just to revisit this portion just a little bit, this is clear, right? We've just proved this. Forget about what I wrote here. Just focus on, we're given the fact that the two the transistors of the inverters are matched. So this, which is Kn, equals Kp, right? That we know. So in this equation, if you take this portion, which is Kp prime W by L, and replace it with this portion, put it here, right? Take this, put it here. Then you have two equations which have Kn prime on both sides. Take that out. Then half W by L 5 by 6 becomes W by L P, or W by L 5 by 6. Take the 2 from here to the other side. It becomes 2W by L N. Okay. So basically we have proved that the W by L of the AND gate transistors, which are also NMOS, remember, these have to be twice the W by L of the inverter NMOS transistors. Okay? Alright, I hope with that most of the confusion is cleared. We have one more problem. Give me a second, I'll be back. Okay, so we finished this, and we have one problem related to D flip-flops. Now this is an interesting problem. We are not actually doing anything like W by L calculations and uh, drain currents calculations and all that. It's just a kind of a descriptive question and a descriptive solution, no numbers to be done. Like I said, for your purpose, this problem is not too important. I'm not going to give you any questions on D flip-flops in the exam, but focus on all the stuff that we studied so far with the SR flip-flops. We've done enough problems, so you now know what kind of questions are important. Mostly they revolve around, how do you calculate the W by L ratios, and also how do you calculate the width of the pulse necessary, the set or reset pulse, how wide should it be to be able to, do the flipping and flopping. That means to change state. So focus on that. This is just something additional, so maybe you'll be interested, maybe not, but don't worry too much if you don't get it. But the interesting part about this problem 1511 is that this circuit is used to create a negative edge triggered flip-flop, D flip-flop. So previously we have seen D flip-flop, it works on the rising edge of the clock, right? This works on the falling edge of the clock. Other than that, there's no difference. The truth table is pretty much like this, is what we have to implement. But instead of the clock showing rising, you can think of it as showing falling. So on the falling edge, whatever is on D has to come out to Q. Okay? So that's what it is. And what the question asks is, if phi is high, right, if the clock is high, what are available at the outputs, Q bar and Q? So you first get Q bar, then you invert that to get Q. So it's different kind of configuration. And the cross linkage, the cross connections that we normally see in latches happens through this pair of transistors, Q1 and Q2, and this pair of transistors, Q3 and Q4. So connecting the output back to the inputs of the other gate happens through these pairs of transistors. So if phi is high, what is the output? If phi is low, then D can be high or D can be low, right? And we know that phi, when it is going low, we want D to transfer to Q. So the explanation for how this happens, also the last question, does this rely on any charge storage, or is it purely static sequential? And the answer is it's purely static sequential. It doesn't need any charge storage and capacitors. And I've given the answers detailed for part A, part B, part B and C. They are like each other. Only thing is the clock is low, D can be either high or low, and in each case you'll see that either this two transistors create a path or these two transistors create a path, and the circuit operation is described. So read it at your leisure. Again, not a very important topic from an exam point of view, but if you want to learn what the difference is between a D flip-flop with a rising edge triggered clock versus a D flip-flop with a falling edge triggered clock, then this problem gives you the answer. Okay. So with that, we have done all the problems of this section also, the flip-flop section, and we have finished week 3 material, which was some advanced MOS topics and flip-flop memory circuits. Okay. All right. Next week we'll move on to week 4.